Good morning and welcome back. Today in Integrated Science, we are going to start talking about solenoids. So we're going to bounce off of our idea of what we talked about the past couple of days with static electricity and the idea how static electricity can create that spark between the protons and the electrons because you have two opposite charges that are being attracted to each other. And then we went in and we started talking about the idea that when you have an electrical current going through a system, that can cause our electrons to flow or electrical current through a chemical reaction occur. And so when we do that, we can also create a small or sometimes large magnetic field. And so yesterday we talked about our magnets and the idea that they have both a north and a south pole, or a positive and a negative end, and those are the areas where they are a lot of force is being applied, where it is coming out and it is the strongest. So kind of linking back to Newton's second law of motion, where we have force and acceleration. So those electrons are coming out, accelerating really fast, creating a magnetic force. And remember that magnetic force is a 3D image that's coming out everywhere. Kind of think we talked about the Earth's magnetic field, and that the Earth's magnetic field is encompassing, it's enveloping the whole Earth. So we're protected from those solar radiations that can come from the sun or any other outside type of material that can come from outer space and harm us in some way, shape, or form. So today we're going to build on that just a little bit, and unfortunately we'll be able to look at the lab online with Faraday, but the idea is that Faraday's law suggested that he was able to figure out the idea that when you have an electrical current, you also have a magnetic field, and that's what we're going to visit today. So I am going to go down to our energy unit, and that's going to populate into our notes where I want to go into magnets and solenoids. And we looked at this yesterday with the magnet aspect. Now we're just going to go back and look at how does this apply with our solenoids. So I'm just going to go ahead and download this for us so it'll make it a little bit easier.
It's a different skill set learning that, how to sell that way.
And let me pull this up.
It's going to be a process.
And so I am going to fast forward just a little bit into our solenoid section. There we go. Maybe here just slightly. There we go. All right. So today, like I said, we're going to now combine the two ideas that both electricity and magnets can be connected, aka meaning that if you have an electrical current, you have also a magnetic field. And if you have a magnetic field, you also have an electrocurrent. And that's going to lead us into then tomorrow starting to talk about our electromagnetic spectrum, in which we have our different types of radiation: radio, infrared, microwaves, visible light, everything that we can see, our UV radiation, X-ray, and gamma radiation. And these are all electrically charged radiation that is coming at us. So we can create them here to visibly see them on Earth, but they're moving all around us right now. You're being able to get a signal through a radiation. If you were to go make something in the microwave, you're radiating that. If you were to break a bone in your body, they would give you an X-ray to double check to see what kind of fracture or if it's a compound break or whatever it is. We're looking at what is that actually happening with the system. So a solenoid is a coil wire with an electrical current moving through it, meaning that it is a iron or sometimes copper or aluminum, whatever type of rod. We in class would have used a nail, and with that we coil around our conductor. So think about our conductors as being copper, once again tin, and other types of metals. So we have this looped around our wire, and then we send a current through the actual rod, and that is going to magnetize or create energy through these coils. So a solenoid is a coil wire with an electrical current in it, meaning that we've got this current moving through. Sorry, I have my email notification up, so we're going to get those every once in a second here. Let's go to the next slide.
Okay.
So the idea is that, I feel like I'm half and half here. There we go. So an electromagnetic or electromagnet, so electricity, magnet, creating a magnet, it's a temporary magnet, meaning that as long as you have an electrical current moving through that iron material, it's going to temporarily create a magnet for you. So in the activity that you're going to do today, you'll be able to put the current through a circular disc, and you're going to be able to see the compass kind of tick back and forth. In class, we would have created, I have nails, we would have wrapped the wire, our copper wire, around the nails, attached each end of the copper wires to a battery, and then tried to magnetize the nail in order to pick up paper clips. So that is a lab that we will do. So once again, an electromagnet is a temporary magnet made by placing a piece of iron inside a current carrying a coil. So the copper wire would have been the current that is carrying that energy. So the copper wire is the coil. The closer the coils, the stronger the magnet gets. So remember, we talked yesterday about magnetic force. So if you decrease the distance, the stronger the magnetic field gets. So if we get those coils really tight around the nail, that's going to create a stronger magnetic field, as opposed to just maybe looping it 4 or 5 times. Then it's still magnetized, but it might not be strong enough to pick up even like the simplest of maybe like a staple, just like one little staple. So think about that. So this is what it says. So when a current flows through a circular loop of wires, the magnetic field lines form all around the wire. So it goes just around with the wire. It's almost like an oscillation, if you want to think about it that way, but it's magnetic lines that are doing that. So it's once again, those electrons and those forces that are being created.
You're gonna do them every day, we'll figure one out.
So short pulses of currents are passed through the coil at a rate of about 100 pulses per second. Each pulse, so once again, it's kind of like if you had your iron rod, you had your wire wrapped around, and you kept like connecting it, disconnecting, pulse, 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 pulse. That's what this is saying here. So short pulses of a current are passed through the coil at a rate of about 100 pulses per second. So it's like super fast. Our best answer, let's look at these. A current around the wire, a magnetic field around the wire, an electric field around the wire, a none. The wire is insulated. So what it's actually doing, it's creating an electric field around the wire. So let's talk a little bit about the idea of the right hand rule, which is a way that we can figure out which way the current is going. So a magnetic field around a current carrying wire forms a circular pattern around the wire. So that's what this picture is once again. So we have energy moving through the wire, and it's creating a small magnetic field. If we wanted this to be stronger, we would coil it to keep that wire really, really close together. And sometimes if you look at like a very intricate type of wire, so maybe some that are running electricity in your house, lots of times they are kind of coiled together so that we get that energy keep going through a system. So when you wrap your hand around the solenoid with your fingers in the direction of the conventional current, your thumb points in the direction of the magnetic north, meaning that if you are thinking about so I have earbuds in today, so it's hooked over here to my laptop and it's running up here to my ears. So the current, we would think, is conventionally coming from my laptop up to my ears. And so if you think about that, if I were to wrap my hand around it, my thumb would point this way, conventional north. Let's say though that I had a speaker on or something like that, it might be running the opposite way. So it's a really simple way of just trying to figure out which way is the current going and where is our magnetic north. And so once again, we could get a compass out and I could hold the compass up to this and we would see the needle tick back and forth just ever so slightly, showing us which way that current is moving to the magnetic north. So let's look at this question here. Which of the following cases where magnetic fields are produced by a solenoid is the magnetic field increased? So remember, if we want to increase the magnetic field, we want to decrease the distance. So let's look at these sample answers here. So a number of coils is increased. The number of coils is decreased. The direction of currents is parallel to the magnetic field. The right-hand rule is reversed. So once again, remember, if we are increasing the coils, we are increasing the magnetic field. So the number of coils is increased if we want to increase that magnetic field. So a wire is coiled several times around an iron bar. An electric current is allowed to flow through the wire. What happens to the wire wrapped around the iron bar? It begins to move, the iron becomes hot, no charge occurs, or it becomes an electromagnet. Clearly, this is what we're talking about, an electromagnet. So once again, you have your iron rod, you wrap the coils around it, and then you charge it with some type of current and it becomes electrically charged. A device that produces the magnetic field by wrapping a wire is our solenoid. So those are some sample questions that you might kind of see on a test just a little bit. So once again, I'm going to let you guys work with that PHET to try to create the electromagnets, and when we get a chance, we'll do this in class where we'll pull out the iron nails and the copper wire and try to create the strongest magnet that we can. Thanks for joining. If you have any questions, feel free to inbox me, and I'd be happy to help answer any questions. Thanks.
So